Now that we know about bond polarity, we're now going to focus on molecular polarity. So whereas bond polarity is between the polarity of one atom to another atom, molecular polarity is overall how polar is the molecule as a whole. Okay, is there a draw of electrons going in one direction versus another, or is it overall balanced? Okay, and it really depends on whether the molecule is symmetric or not as far as the electrons go. There are two types of polar molecules. One is nonpolar and one is polar. Nonpolar, just like with nonpolar bonds, is where it is completely symmetric or there's an equal distribution of charge. Okay? You do need to know and memorize that the possible shapes that could form a nonpolar molecule, or where the electrons are completely distributed evenly, are these three. We've got linear, trigonal planar, and tetrahedral. Okay, now these are possible symmetric shapes. So just because it has one of these shapes, it does not necessarily mean that it is going to be nonpolar. It just has the possibility. A polar molecule, on the other hand, has an uneven or unequal distribution of charge. And what that means is that there's a pull of electrons going in one way versus another. And these are definite shapes that will always have a polar molecule. If you ever have a bent or a trigonal pyramidal shape, you are definitely going to have a polar molecule. There are a few steps that you're going to want to follow in order to determine whether it's going to be a polar or nonpolar molecule. The first one is you're going to check, is it a hydrocarbon? Well, let's break down what the heck a hydrocarbon is. If I look at what the word hydro, that looks like hydrogen, and carbon is carbon. So it's a molecule that has only carbons and hydrogens in its makeup. So if you ever see any CH4s, or if you see C2H6, anything where all you see is carbons and hydrogens, you have something called a hydrocarbon. And if you have a hydrocarbon, you can immediately say that it is a nonpolar molecule. When that happens, that is saying that all of the electrons are shared amongst the elements equally overall. If it's not a hydrocarbon, then you are going to have to determine the molecule's Lewis dot structure. So you are literally going to have to draw the Lewis dot structure for that particular compound. The next thing you're going to do is, after you've drawn the Lewis dot structure, you're going to figure out the shape of the molecule. After that, you are going to ask yourself, is this shape symmetric? If it is symmetric, meaning one of those three particular shapes, meaning linear, trigonal planar, or tetrahedral, then you need to move on and still try to figure out if it's a polar or nonpolar molecule. If it is asymmetric, then you know automatically that the compound is polar. And remember, those particular ones were bent and trigonal pyramidal. Okay, so if it's those shapes, then you can automatically say it is going to be a polar molecule. If you have one of the symmetric shapes, linear, trigonal planar, or tetrahedral, you then need to ask yourself if all of the atoms are attached to the central atom are the same. If it is yes, then we are going to go with that it is nonpolar. If it is no, then the molecule is going to be polar. So there is a draw going towards one side of that molecule. All right, so here's just another visual of this. So first, if we're given these two structures, you're going to identify, is the molecule a hydrocarbon? Looking at the structure on the left, I do notice that I have carbons and hydrogens, and I have nothing other than carbons and hydrogens, so check, it is a hydrocarbon. Because of that, I know that it is going to be nonpolar molecule automatically. On the structure on the right, I have hydrogens, which is good, but I do not have that only carbon. So therefore, this would be not a hydrocarbon, so I would need to go on and ask step 2. In step 2, I would be determining what is the shape of the compound. So I would need to look at my shape sheet, okay, which we've already used and done, and I would try to identify it based off of that central atom, what shape it was. After that, I would need to ask myself, is this shape symmetric? Is it symmetric would be if it is linear, if it is trigonal planar, or if it is tetrahedral. If it is one of those, I need to move on and ask myself about this, what is attached to those particles, or the molecule, or the atom, sorry. If it is trigonal pyramidal, or bent. Sorry, I guess this linear should have been colored too. Whoop, not in yellow, in purple, silly. All right, if it was bent or trigonal pyramidal, I can automatically say these are going to be polar compounds. Okay, if it was one of the ones that were circled in purple, then I would need to move on, and I would need to ask myself if the atoms attached to the central atom were the same or not. So looking at these different structures, I have SOCl2 and I have SO3. I notice that this is going to be a trigonal planar shape, both of them. So what I need to do is ask myself, is the central atom attached to the same three things, or is it attached to somewhat of a different thing? If I look at the SO3 on the left, I notice that S is connected to three different O's. Okay, so therefore, because it is attached to the same thing, it is entirely symmetric, and therefore it is going to be considered nonpolar. On the other hand, if I look on the right, and I notice that that S is connected to one O and then two Cl's, it is not connected to the exact same things, so therefore it is going to be asymmetric, which means it is going to be deemed as a polar compound. If I look at overall this electron distribution for both of them, and I were to draw a cloud over them, what I would notice is that for my nonpolar compound, that there is really a relatively equal distribution amongst the whole compound as a whole. It's symmetric, which means that I can divide it up amongst both axes, and it would look the exact same, okay, as far as my electron distribution. On the other hand, when I look at my SOCl2, which has a polar distribution of electrons as a molecule, I notice that there is a lot more electrons concentrated on the bottom by the Cl's than at the top by the O's. And therefore it is a polar, and the electrons are being pulled towards that Cl bottom, as opposed to the SO3, they are perfectly being evenly distributed. All right, now what we are going to be doing is applying this comparison to an actual two compounds. So first, you need to ask yourself, is the molecule a hydrocarbon? I'm going to be looking at PCl3, and PCl3, I see that there's chlorines and phosphoruses, which is not a hydrocarbon. I don't have a hydrogen or a carbon. And in CCl4, I do have a carbon, but I have 2 or 4 chlorines, so therefore it is not a hydrocarbon. If it was, I would say that it was nonpolar and call it a day, but because it is not, now I need to draw the Lewis dot structure. So what I do is I drew the 2 Lewis dot structures for PCl3 and CCl4. All right, the next thing you need to do is, after you've drew them, you need to determine the molecule's shape. So looking at your shape sheet, I'm going to notice that P has 1 lone pair and is attached to 3 different things, which would make it a trigonal pyramidal, whereas my CCl4 is attached to 4 different things with 0 lone pairs. Looking at that shape sheet, I would notice that it was a tetrahedral. The next thing I would need to do is ask myself if that shape is symmetric. For the trigonal pyramidal, it is under my asymmetric sheet, so I know immediately that it is asymmetric or not symmetric, so it would be considered a polar molecule, meaning that there's a pull of electrons going in one given area, whereas the tetrahedral is a part of my symmetric shapes along with trigonal, planar, and linear, so I know I'm going to need to move on for this guy, for CCl4. But right now I know that PCl3 is considered polar, and I can ignore that from now on. All right, so now that I have to focus on just CCl4, I have to ask myself the final question: are all the atoms attached to the central atom the same or not? If they are, it is going to be considered a nonpolar compound. If they are not, it is going to be considered a polar compound. In this case, C is connected to 4 different elements, and all of them are chlorine, so therefore they are all the same. So this compound is very symmetric, which means that it is a non-polar compound. All right, hopefully you understand molecular polarity, at least briefly, and we'll be focusing more on class.